Most of the structural columns are not only subject to axial compression forces, but also subject to bending moments. These structural members are called beam columns. In this presentation, we will go over the concept of steel beam columns and present the relevant equations used by the American Institute of Steel Construction, AISC. As we mentioned earlier, beam columns are structural members subjected to axial compressive force and bending moments. Now let's get started with uniaxial bending and axial compression and consider the following beam column and assume that the beam column is braced in a way that buckling occurs about the x-axis. Uniaxial bending moment is a moment that acts on one axis of the cross-section. This is our beam column, and this beam column is subjected to axial compressive force Pu and uniaxial bending moment Mux. It's very obvious that the bending moment Mux is about the x-axis. The result will be combined stresses of axial compressive stress and bending stress. The axial compressive stress will be Pu over Ag, and the bending stress will be Mux over Zx, where Pu is the factored axial load, Ag is the gross area of the cross-section, Mux is the factored bending moment about the x-axis, and Zx is the plastic section modulus with respect to x-axis. The governing interaction equation will be Pu over Ag plus Mux over Zx is less than or equal to Fy. The students are advised to go back to any textbook in mechanics of material to refresh their memories on this particular topic. Please note that this equation represents the right side of the cross-section since both axial and bending stresses are compressive. Now, if we divide both sides of this inequality by Fy, we will get this equation. If we substitute Pn for Fy Ag and Mnx for Fy Zx, we will get this equation, where Pn is the nominal axial compressive strength, Mn is the nominal moment strength, and in this case, Mn is equal to the plastic moment. In LRFD method, design strengths should be used rather than nominal strength. Therefore, the reduction factors phi C and phi B should be included, and the last equation can be rewritten as two formulas are given in the AISC specifications, one for large axial load and one for small axial load. If the axial load is large, in other words, if Pu over phi C Pn is greater than or equal to 0.2, the bending moment term is slightly reduced. Here, the bending moment term is reduced by 1/9. For small axial load, in other words, if Pu over phi C Pn is less than 0.2, the axial load term is significantly reduced. Here, the axial load term is reduced by 1/2. Next, let's consider biaxial bending and axial compression. Biaxial bending moment is a moment that consists of two moments acting on the principal axes of the cross-section at the same time. Here, we have a beam column subjected to axial compressive force Pu and two bending moments. The first bending moment is about the x-axis MUX, and the second bending moment is about the y-axis MUY. The governing interaction equation will be Pu over Ag plus MUX over Zx plus MUY over Zy is less than or equal to Fy. Now, if we repeat the steps that we followed to solve the uniaxial bending and axial compression, we will get an inequality similar to what we have here. Again, two formulas are given in the AISC specifications, one for large axial load and one for small axial load. If the axial load is large, in other words, if Pu over phi c Pn is greater than or equal to 0.2, the bending moment term is slightly reduced. Here, the bending moment term is reduced by 1/9. For small axial load, in other words, if Pu over phi c Pn is less than 0.2, the axial load term is significantly reduced. Here, the axial load term is reduced by 1/2. Two types of structures have been considered in this chapter: non-sway frames or braced frames, and sway frames or moment frames. A non-sway frame is a frame whose ends cannot translate with respect to each other, which can be done using shear rolls or diagonal steel sections. A sway frame is a frame whose ends can translate with respect to each other. The applied forces are resisted by the bending moment and shear strength that are inherent in its members and the connecting joints. The presence of the external loads produces primary moments and can be calculated using conventional methods of structural analysis such as slope deflection, moment distribution, and stiffness methods. The presence of the axial load in the columns produces secondary moments, and these additional moments must be accounted for. In the American Institute of Steel Construction AISC Design Manual, secondary moments are accounted for by introducing two amplification factors, B1 for non-sway condition and B2 for sway condition. These two factors are derived from considering P small delta and P capital delta effects. Now let's consider a non-sway frame and investigate the P small delta effect. The following beam column is part of a non-sway frame and subjected to an axial compressive force P and a bending moment M. The primary bending moment M will cause the column to deflect an amount of delta 1. Now, let's cut a section at distance x from support A. If the beam column is in equilibrium, then this segment should also be in equilibrium, and a force of equal magnitude but opposite direction to the force at support A must act at this point. The result will be a couple. The value of this couple is P times delta 1. The couple will cause additional lateral displacement or deflection along column depth. The lateral deflection or displacement will increase to delta 2 when the structure reaches equilibrium in the final displaced position. Therefore, the total displacement delta will be delta 1 plus delta 2, and the corresponding moment, or the secondary moment, M secondary equals delta times P. Now let's consider a sway frame and investigate the P capital delta effect. The following beam column is part of a sway frame and subjected to an axial compressive force P and a bending moment M. As we know, a sway frame is a frame whose ends can translate with respect to each other. The primary moment M will cause the column to deflect an amount of delta 1. Now, let's cut a section at distance x from support A. If the beam column is in equilibrium, then this segment should also be in equilibrium, and a force of equal magnitude but opposite direction to the force at support A must act at this point. In other words, sigma fx equals 0, where x is the vertical axis. The result will be a couple. The value of this couple is P times delta 1. The couple will cause additional lateral displacement or deflection along column depth. The relative lateral deflection or sway will increase to delta 2 when the structure reaches equilibrium in the final displaced position. The total displacement delta will be delta 1 plus delta 2. The corresponding moment will be M secondary, or the secondary moment will be delta times P. The philosophy being used by the AISC to account for secondary moments are the use of amplification factors. These factors should be multiplied by the primary moments obtained from first-order analyses. Now let's jump into the moment amplification factor for non-sway frames and consider a structural member with initial crookedness or deflection and subjected to an axial compressive force P. The initial crookedness, which represents the effect of the primary moment in the beam column, can be approximated by y0 equals E sine pi x over L, where L is the length of the structural member, in this case is a beam column, E is the mid-span deflection of the structural member, and this is the maximum deflection. Y0 is the deflection of the structural member at any distance x measured from the left support. It's very obvious that the deflected shape was modeled as a sine wave. As we mentioned earlier, to maintain equilibrium, we have to have an axial force P at distance x measured from the left support. The result will be a couple and the value of this couple is P times Y0. This couple will cause additional lateral displacement or deflection. The lateral deflection will increase to Y when the structure reaches equilibrium in the final displaced position. The moment curvature relationship is the second derivative of y with respect to x equals minus m over EI, where m is the total moment and EI is the flexural rigidity. The total moment m can be expressed as P times y0 plus y. Now, if we substitute the total moment m into the moment curvature equation, we will get this equation. This equation can be rewritten as shown in equation 2. Equation 2 is a second-order linear non-homogeneous differential equation. With the aid of the following two boundary conditions, at x equals 0, y equals 0, and at x equals L, y equals 0, equation 2 can be solved, and the result will be y equals b sine pi x over L, where b is a constant. Remember, y is the final displaced position when the structure reaches equilibrium. Substituting equation 3 into equation 2, we will get this equation. Please note that the deflection y is measured from y0. Solving the previous equation for b, the constant b can be calculated as shown in equation 4, where PE is the Euler or elastic buckling load. Now, if we substitute equation 4 into equation 3, we will get equation 5. Now, if we substitute equation 1 and equation 5 into the equation of the total moment m equals P times y0 plus y, the total moment can be found as shown in equation 6. Since the maximum moment occurs at x equals L over 2, the maximum moment can be expressed as the previous equation can be simplified and rewritten as shown in equation 7. Notice that the equation of maximum moment consists of two parts, m0 and 1 over 1 minus p over pe, where m0 is the unamplified maximum moment and 1 over 1 minus p over pe is the amplification factor. AISC Design Manual uses a modified version of this term, and the amplification factor in nanoswave frames is denoted as B1 and can be expressed as B1 equals Cm over 1 minus Pu over Pe1. B1 should always be greater than or equal to 1, where Pe1 equals EI star is the reduced stiffness, and Cm equals 0.6 minus 0.4 times M1 over M2. Where M1 over M2 is the ratio of the bending moments at the ends of the member,
the absolute value of M1 is less than or equal to the absolute value of M2. In other words, the absolute value of M2 is greater than or equal to the absolute value of M1. M1 over M2 is negative for members bent in single curvature, and M1 over M2 is positive for members bent in double or reverse curvature. Two things are worth mentioning here. One, members bent in single curvature are more critical than members bent in double curvature. Why? Because single curvature produces higher bending moment than double curvature. 2. If the bending moments at the ends of the member are equal and the member is bent in single curvature, the value of Cm is 1. The reduced stiffness EI star equals 0.8 tau b times EI, where tau b is the stiffness reduction factor. Tau b equals 1 when Pu over Py is less than or equal to 0.5, and equals this term when Pu over Py is greater than 0.5. For transversely loaded members, Cm can be taken as 1, or 1 plus psi times Pu over Pe1. The value of psi can be calculated using this table. For example, a beam column with hinge supports at both ends and subjected to uniformly distributed load. Psi equals 0 and Cm equals 1. A beam column with one end is fixed and other end is hinge and subjected to uniformly distributed load. Psi equals negative 0.4 and Cm equals 1 minus 0.4 times Pu over Pe1. Now let's go over the details of the factor Cm and investigate the maximum no translation moment M and T. As we know, an anisway frame is a frame whose ends cannot translate with respect to each other, and the end moments are either in the opposite direction or the end moments are in the same direction. In both cases, the maximum amplified moment can occur either at one end or anywhere along the length of the column. For example, when the end moments are in the opposite direction, the maximum amplified moment will occur at this end or anywhere along the length of the column. A very similar scenario is observed when the moments are in the same direction. The maximum amplified moment will occur at this end or along the length of the column. The purpose of introducing the factor Cm is to account for all these cases and come up with equivalent moments at failure. Now let's move on to sway frames and consider the following structure. This structure is subjected to two axial forces Pu and one lateral force Hu. If we use any structural analysis software, we can show that 1. The sum of the column moments in a sway frame is equal to the height of the frame, Lc, times the applied lateral load, HU. 2. Delta U1, which is the lateral displacement, and HU, which is the lateral load, are proportional, where eta is the constant of proportionality. Before we proceed any further with this topic, the students should know, understand, and memorize these two equations very well. This figure shows the column moments in a sway frame. Again, a sway frame is a frame whose ends can translate with respect to each other. The figure on the left side of the slide shows the loads on a sway frame, while the figure on the right side of the frame shows the equivalent magnified lateral load. Please note that the moment sigma pu times delta u1 in a given story can be represented by lateral or shear forces sigma pu times delta u1 over LC. Let's assume that this figure represents the summation of forces acting on all columns in one story of a multi-story building frame. The primary moment will cause the column to deflect an amount of delta 1 U. The couple, sigma pu times delta 1 U, will cause additional lateral displacement or deflection along column depth. The final displaced position when the structure reaches equilibrium will be delta 2 U. The corresponding magnified moment will be B2 times sigma MLT. The rationale for using the total story load and strength in calculating B2 is that if side sway is going to occur, all columns in the story must sway simultaneously. Before we go deeper into sway frames, we need to discuss the maximum lateral translation moment, MLT, caused by lateral or by unbalanced gravity loads. The maximum primary moment resulting from the side sway is almost always at one end. Moreover, the maximum secondary moment from this side sway is always at the end. As a consequence of this condition, the maximum primary and secondary moments are usually additive, and there is no need for the factor Cm. In other words, Cm equals 1. Now let's jump into the moment amplification factor for sway frames. From first-order analysis, we have proven that the sum of the column moments in a sway frame is equal to the height of the frame, LC, times the applied lateral load, HU. Does this equation ring a bell? We also have proven from first-order analysis that the first-order sway deflection delta 1U and the lateral load HU are proportional, where eta is the constant of proportionality. Eta can be written as delta 1U over HU. Now let's consider the final displaced position when the structure is in equilibrium. The sway deflection at equilibrium is delta 2U. The amplified moment in this case will be B2 times the summation of MLT1 and MLT2. This term should equal LC times HU, which is the primary moment, plus the summation of PU times delta to U. This term represents the secondary moment. Now we can solve equation 9 for B2. Now if we substitute equation 8 into this equation, we will get equation 10. Notice that B2 in equation 10 is function of delta 2U, and delta 2U is unknown. The equivalent magnified lateral force equals HU plus sigma PU times delta 2U over LC. Sigma PU times delta 2U over LC is the equivalent lateral force of the axial loads. Delta 2U equals eta times the equivalent magnified lateral force. Why? Because lateral displacements are proportional to the lateral forces. Now, if we substitute equation 11 into equation 12, we will get this equation. If we substitute delta 1U over HU for eta, simplify the equation and rearrange the terms, we will get equation 13. Note that delta 2U is function of delta 1U in equation 13. The moment amplification factor for sway frames B2 can be expressed as shown in equation 14. If we substitute sigma PE2 for HU times LC over delta 1U, we will get B2 equals 1 over 1 minus sigma PU over sigma PE2. This term should always be greater than or equal to 1. The American Institute of Steel Construction Design Manual uses a modified version of this equation, where P story is sigma PU and PE story is sigma PE2. PE story equals Rm times HL over delta H, where Rm equals 1 minus 0.15 times PMF over P story, where P story is the sum of factored axial loads for all columns in the story under consideration. PE story is the total elastic buckling strength of the story under consideration. PMF is the sum of vertical loads in all columns in the story that are part of moment frames. L is the story height. Delta H is the drift or sideway displacement of the story under consideration. And delta H over L is the drift index. The drift index ranges between 1 over 500 and 1 over 200. Notes: if there are no moment frames in the story, PMF equals 0 and Rm equals 1. If all of the columns in the story are members of moment frames, then PMF equals P story and Rm equals 0.85. The ratio H over delta H can be based on either factored or unfactored loads. Methods of analyzing sway structures. Method 1. Perform structural analysis in which the side sway of the frame is prevented. The resulting moments are the no translation moments M and T. consider using fictitious horizontal support if needed. Don't worry, we're gonna go through all that in just a few seconds. Perform structural analysis in which the side sway of the frame is not prevented. The resulting moments are the lateral translation moments, MLT. Consider using artificial joint restraint if needed. Method 2. Perform structural analysis in which the frame is assumed to be braced against side sway. The resulting moments are the no translation moments, MNT. Perform structural analysis in which the frame is assumed to be unbraced. The results of the first analysis are subtracted from the second analysis to obtain the lateral translation moments, MLT. Figure A shows an unbraced frame subjected to both gravity and lateral loads. The moment MT in member AB is computed by using only the gravity loads. Because of symmetry, no bracing is needed to prevent side sway from these loads. The moment is amplified with the factor B1 to account for the P small delta effect. MLT, the moment corresponding to the sway caused by the horizontal load H, will be amplified by B2 to account for the P capital delta effect. In figure B, the unbraced frame supports only a vertical load. Because of the unsymmetrical placement of this load, there will be a small amount of side sway. The moment MT is computed by considering the frame to be braced, in this case by a fictitious horizontal support, and the corresponding reaction called an artificial joint restraint, AJR. To compute the side sway moment, the fictitious support is removed, and a force equal to the artificial joint restraint, but opposite in direction, is applied to the frame. In cases such as this one, the secondary moment P capital delta will be very small and MLT can usually be neglected. If both lateral loads and unsymmetrical gravity loads are present, the AJR or artificial joint restraint force should be added to the actual lateral loads when MLT is computed. In conclusion, unbraced frames exhibit both non-sway and sway behaviors. Therefore, both MNT and MLT should be accounted for on the member. The American Institute of Steel Construction AISC Design Manual presents two general equations to calculate the required moment strength and axial load, taking into account the effect of P small delta and P capital delta. By now, we are all familiar with the notations below. AISC approaches for determining the required flexural and axial compressive strength. 1. The direct analysis method. In this method, the second-order analysis or approximate second-order analysis is required. The member stiffnesses are reduced, and the effective length factor of K equals 1 is used. 2. The effective length method. In this method, the second-order analysis or approximate second-order analysis is required. The effective length factor K must be determined. and the member stiffnesses are not reduced. 3. First order analysis. In this method, effective length factor of K equals 1 is used, and the member stiffnesses are not reduced. Please note that a new presentation that contains 5 solved examples on beam columns and steel frame structures will be uploaded soon.